at this time for everyone. And Emily, I'll let you kind of keep an eyeball on the chat as well, in case you know, if somebody has a question, we have to put that in the chat. As usual, we'll kind of do that. And at this time, team, I'm going to go ahead and share my screen.
Well, and as Joel's bringing that up, how many of you guys had a chance to get your hands on these units yet, or seen anything like it? A couple of you guys, or one? I saw one at least. So that's good to hear. We've got a lot of competitive advantages with these units, and I really like Joel's got a great training here that we're gonna go over some of the details to make sure you guys are comfortable. And feel free to interrupt, Joel. I do it all the time, so no worries.
Yeah, absolutely. Okay, so we're trying to get our little window moved here really quick. Give me just a second to get that done. Want to make sure that the PowerPoint is going to run okay. Okay. All right, everyone should be able to see that screen okay.
Yes.
Everyone can see the screen good? Okay. Okay. Well, let's go ahead and get started then. So this morning we're going to start out with the HMH7, which is a 17 SEER heat pump. It's nominal 17 SEER. And by the way, it'll actually hold that SEER rating all the way up to the largest model. So that's pretty cool. And a couple things I'd like everybody to remember real quick too, also is that the service fittings on these things are actually 5/16 fittings. So what you're going to want to do is you're going to want to make sure and have those adapters that go from 5/16 flare to 1/4-inch flare for your service hoses. And you guys have seen these. Robinair and Yellow Jacket and different companies make them. But they're the same kind of fitting that you'll see like on mini splits. And I want to stress this to everybody. These units are not mini splits. They're not a mini split product. However, they kind of look like a mini split product, but you're going to wire them up and you're going to take, suction line out to it and liquid line out to it, insulate your suction line. You're going to treat it just like a regular old heat pump. You're going to pipe it in like you always did. Good refrigeration practice, of course, keep the lines nice and clean and dry and so on, and get a good double evacuation. So you're just going to treat it like any other heat pump. But just please remember, you're going to need this little adapter to go from your 5/16 fitting on the outdoor unit to your 1/4-inch hose for your service valves, if that makes any sense. So just be sure and kind of keep that in the back of your brain when you're putting these things in. The other thing we like to talk a little bit about on the unit as we kind of move forward with it a little bit on some of the ratings and stuff like that, is if you take a look at it, you're going to notice that the outdoor unit and the indoor coil, if you will, or the indoor, there's a pretty wide operating range there from a minimum max. So to give an example, on the outdoor coil for cooling, you can actually go down to 35 degrees outside for cooling, up to 122 degrees on cooling. And in the heating mode of operation, this thing will operate down to -5 degrees outside. And so, which is pretty nice. And maximum heating would be 75 degrees outside. So you can kind of look at those charts a little bit. In addition, down below, we went ahead and gave an example of some of the rating examples. And this, by the way, is right there in the application guide that you can get the product information off a Navigator. But you'll see this is just a typical 3-ton model. And as you take a look at it, even though the actual rating on the thing, at 3 tons is going to be like 17.5 SEER for this particular model and that particular air handler combination, you're going to notice that even as you start getting down into the reduced capacity of the thing, it's still going to have a really high EER. And that's something that's pretty remarkable if you think about it, because, the standard full-blown EER on the thing is 9.0. But when you're down there, like half capacity, I mean, it's like 34.5. EER. It's just crazy high EERs. Now, guys, remember that EER is going to be your energy efficiency ratio, the amount of work that's being done basically for the amount of energy that you're utilizing. And so very, very high EER ratings in that partial load application. So these units work very, very well, give you lots of energy efficiency, lots of comfort, and they're just a great unit. Any questions or comments on the things that we've talked about so far? Everybody good?
We were good, so.
Okay. Okay, so this time, go ahead. Do we have a question or a comment?
Now you're just saying they're a quiet bunch.
Okay, okay.
It's a little early, huh? Everyone got their coffee?
Yeah, everybody's got their coffee. That's great. So basically this time what we're going to do, team, we're going to take a look at some low voltage wiring diagrams, and specifically we're going to dig in and start in with the AE air handler. And we're going to be just looking at some simplified block wiring diagrams. Now remember, the AE air handler has no physical terminals, but it's equipped with a pigtail connection. Now it should be noted also that the same wiring that we're doing right now, and this slide's a little bit dated because I've got AE air handler on here, but the actual wiring and stuff is going to be identical on our new JHET air handler. So the JHET air handler, a little different designation. It has an A coil inside of it instead of the N coil. But as far as electrically, it's going to wire exactly like the AE air handler. We're also going to be discussing this single pole double throw relay kit on the indoor unit. And what that kit number is, that's a HMH7AK001, and it's going to be recommended. We're going to recommend that kit for convenience and supplied parts. Now, it should be noted that if you have I'm not going to read all those numbers again, but if you have a 002 kit, so there's a 001 kit, which is just a single relay. The 002 kit's a relay kit that's got two little relays on it. But it should be noted, if let's say you only have a 002 kit available, you can still utilize it. It's kind of a universal kit. It's just you won't use one of the relays on the 002 kit in this application. Now put this in your back pocket, and please remember this. On any of our variable speed products, any of the variable speed products, with the exception of our brand new JHV VT air handler, which is a variable speed air handler, you have to have that 002 kit. So to give an example, if I have a variable speed furnace and we're going to be hooking this up to a variable speed furnace, I need to have this 002 kit. So the 002 kit has to be used with the variable speed product, the exception being the new variable speed air handler only. But if you have a variable speed furnace, or if you have an older variable speed air handler like an AV type of air handler, not the JH, but the AV type of air handler, you're going to have to utilize that 002 kit. So kind of keep that in the back of your brain, that these kits are going to be utilized on all of our products except the brand spanking new JH VT air handler. It's got configuration on the board itself where you can set up the functionality of this relay kit, but everything else has to have these relay kits in order to operate properly. Any questions or comments on that so far? Emily, did you have a question on that by chance?
No, I was just gonna check with the guys at Mullen if you're typically putting in dual fuel application, or you using the air handlers quite a bit.
They're using the air handlers quite a bit.
Okay, so this is going to be important that you keep this in your brain then. The JHET, or if you have like an older AE air handler like we're discussing now, you have to have that 001 kit. And if you have like a TME furnace or a TMY furnace, you'll need the kit. And so just kind of keep that in the back of your brain, that the only product that does not utilize this kit, or one of these kits, is the new variable speed air handler. The JHVT has functionality on the board where you can eliminate the need for these relays, but that's the only product. So just remember, these relay kits are going to be utilized. You'll see here in a few minutes when we start getting into some of the block wiring diagrams. These relay kits are utilized for airflow management. The other thing we want to make sure that you have, because this is a heat pump, we want to make sure that your heat pump thermostat, the heat pump thermostat, is configurable for BO selection for reversing valve operation. Now, this is really important. You guys put this in your back pocket one more time. This is the only heat pump in our inventory, in our champion lineup, that utilizes the B terminal to energize the reversing valve in the heating mode. Let me say that one more time. All of our other heat pumps utilize the O terminal to energize the reversing valve in the cooling mode. So your normal, champion heat pumps, your commercial heat pumps, and so on. But this product utilizes the B terminal to energize the reversing valve in the heating mode. So it's not bad, it's just different. We just got to keep that in mind, that we have to have a thermostat that's going to be compatible for either B or O selection on the heat pump for reversing valve operation. So just kind of keep that in the back of your mind when you put these in, and as we start going through some of the wiring diagrams and the block diagrams, that we're going to utilize the B terminal to energize the reversing valve in the heating mode of operation. So with all that said, let's go ahead and take a look at some of these block terminals. You're going to notice that on the terminals themselves, again, we've got a heat pump thermostat on the left-hand side there that does have the B capability. And as we kind of move through, you're going to notice B goes from the thermostat to the outdoor unit. W2, if you have an air handler with heat strips, W2 would be your second stage auxiliary heat, and that'll go from the thermostat directly to the second stage. And then on the first stage auxiliary heat, your W1 input will go all the way through from the thermostat to the indoor unit to the outdoor unit. Now remember, guys, when you have a heat pump, when it goes into the defrost mode, we're going to bring those heat strips on via that W1 on the indoor unit. So this is why we have to have that W input from the outdoor unit to come in and energize the heat strips during defrost mode of operation. The Y terminal is going to be our compressor call. You'll see that goes from the thermostat outside. That'll be for our compressor call. You'll also note that on the AE air handler, oftentimes, if it's equipped, some models of the AE air handler, they'll have a yellow wire on the ECM motor. Go ahead and remove that yellow wire off the ECM motor, because we're going to be utilizing the speed taps on this motor as we need it with the relay and so on. We'll get to that in a little bit. So if it does have a yellow wire, go ahead and remove that yellow wire. C is 24 volt common. It slides all the way through from the thermostat to the indoor unit to the outdoor unit. R is 24 volt hot from the thermostat to the indoor unit. Now this is really important, guys. We do not take that R terminal, that 24 volts outside, because the way the outdoor unit is configured and designed, it doesn't need 24 volts to it all the time, from the indoor unit. So we do not take R outside. In addition, we don't take G outside. Obviously, that's just going to be your fan wire. That's pretty much that's pretty standard in the industry. G is your 24 volt fan connection from your thermostat to the indoor unit. And typically, and when I say typical, now if you want to select a different speed tap on that motor, you can. But typically, we're going to see that G is going to be hooked up to the lowest speed tap, so that what's going to happen if the homeowner decides to have air circulating in the house all the time, they'll just go turn the fan to the on position on the thermostat sub-base assembly, and it'll bring the fan on low speed just for air circulation. That's typically how we see that hooked up. Now you'll notice there's that relay that we talked about, that 001 relay in this kit. So the 001 relay has just the one little relay on the board, and I'm not showing that board. This is just a simplified block wiring diagram. But one side of the relay coil goes to S1. Now S1, which we'll talk about in a little bit more, but S1 is an output from the outdoor unit to switch that relay when it wants reduced airflow. The other side of the relay coil is going to go up to the common terminal, or you're going to tie it onto the common wire. And what that's going to do, that completes the circuit for the relay coil itself. So basically, anytime we have an S1 demand, it's a 24 volt output from the outdoor unit. Anytime we have an S1 output, it's going to energize that relay and switch that coil. Energize the coil and switch the relay is what it'll be doing. So the actual contacts themselves on the relay, what we're going to do, we're going to take 24 volt from the Y terminal, and we're going to take that down to the common switching terminal on the relay. So we're feeding power to the common of the relay anytime we have power to the compressor outside or anytime we have a compressor call on Y. Then we're going to take on the ECM motors, we start wiring that ECM motor up. We're going to take the high speed tap off that ECM motor. We're going to take it up to the W1 input. Now, the reason we do that is we want to make sure that anytime we have a auxiliary heat call, we're going to drive that fan to high speed. And this is very typical that you'll see most of the time. You'll have like your high speed tap is going to be for your auxiliary heat call. That way you don't want to overheat the heat strips and so on. Now remember, guys, on an ECM motor, any kind of ECM motor, those high efficiency motors, they've got speed taps on them. In this case, they just have speed taps that you can change. But remember, if it has more than one speed command going to that motor, which it could have on a heat pump, you could have like a low airflow command, and then all of a sudden you're going to have a auxiliary heat command, for instance. And so if that's the case, any ECM motor, if it has more than one speed command, remember, guys, it's just going to drive that motor to the highest speed command that it's receiving. And so that's an important thing we have to remember about all ECM motors. And that ECM motor, that's just a fancy name for the high efficiency motor. That's an electronically commutated motor. That's what ECM means. But if you have multiple speed taps on it, it'll just automatically go to the highest speed command that it's receiving. So this is why we can have multiple taps on this motor, and it doesn't hurt it to have, more than one speed command. So that's pretty cool. So the high speed tap typically is going to go to your auxiliary heat input. That way it'll drive that motor to high speed anytime you have an auxiliary heater. If the unit goes into defrost, remember, we're going to bring the heat strips on during defrost on a heat pump as well. The normally closed contact, you're going to go over to that ECM motor and you're going to select the speed tap off the normally closed contact of that relay to give you 100% cooling airflow. So with the unit just coming on right now with the relay de-energized, we're going to drive it to high speed airflow. However, on the normally open contact of that relay, we're going to go over and select a speed tap for about 60 to 65% airflow. So here's the logic of that relay. When the outdoor unit, because it's a modulating unit outside, but we wire it very simply with 24 volt. But the outdoor unit, when it makes some intelligent decisions and it starts to modulate back, when it gets back to about 60 or 65% capacity, it'll energize that S1 output, switch the relay, and go to a lower airflow inside. So the relay, what it's for, is to allow the outdoor unit to command reduced airflow when it reaches that point of capacity where it needs to have the lower airflow to better match the airflow to the capacity of the unit. Now, guys, a little side note. The HMH7 will modulate from 35 to 100% capacity. So when it gets around that 60% capacity, as it starts screwing the capacity down, as it starts getting milder outside or the load in the house starts being reduced and so on, what'll happen, it'll make intelligent decisions and it'll go ahead and switch that relay and give us reduced airflow when we have reduced capacity. And it's all about comfort and humidity control. That's all about it. That's what that whole airflow scheme is all about. So as we take a look at it, and we'll show you an animation here in a minute or two, but as we take a look at the basic block wiring diagram, do we have any questions or comments at this point?
Looks like we're all good.
Everybody good? Okay. All right, so let's go ahead and talk a little bit more about this. You're going to notice, let me do that animation one more time. Let me back up. So when I get an S1 output from the outdoor unit, bang, that we energize S1 to 24 volt signal. We switch the relay, and we'll notice that S1 input from the outdoor unit actually commands reduced airflow. So there's high airflow again, just sitting there running with a Y call. Bang, when the outdoor unit hits the point of capacity where it says, hey, I want reduced airflow, it'll generate that S1 signal, switch that relay, and give us reduced airflow on the indoor unit. Now, it should be noted, if I get a W1 call during this time, so let's say we're at reduced airflow, and I get an auxiliary heat call, and that indoor blower motor, that ECM blower, has a high-speed command. Well, hang on a second. The high-speed command is greater than the S1 command we have right now with reduced airflow, which is actually 65% airflow. It will automatically drive that motor to high speed. Because remember, anytime you have an ECM motor with more than one speed tap being commanded at one time, it will always go to the highest speed tap that's being commanded. So an example would be if I had a W1 auxiliary heat call, bang, it'll go ahead and just go to that speed tap because it's a higher speed tap. In addition, you're going to have a W1 call or an auxiliary heat call during defrost cycle. So even if we were at reduced airflow and we go into defrost, what's going to happen? The outdoor unit's going to drive to 100% capacity, and it's going to drive the indoor airflow to the speed tap that we have for W1, typically on high. So here we are defrosting the unit now. The outdoor unit's in the air conditioning mode. We're defrosting the unit. You guys know how a heat pump works. And we're going to melt the ice off the outdoor unit, and we're going to energize the heat strip so we don't freeze the homeowner out during defrost. So any questions or comments on the logic of the relay and how all that works on the indoor and the outdoor product before we start looking at some other block wiring diagrams to consider? Everybody good?
So anytime the auxiliary heat is energized, we're going to lose the variable speed in the 35 to 100% capacity that the outdoor unit's looking for.
That's a good question. Not specifically. So what's going to drive the outdoor unit when we go to defrost will be at 100%. But if we're cruising along, say at a 70% capacity, and we get an auxiliary heat call, that W1 call will not drive the outdoor unit to 100%. And so that's a good question. That's a fine point there. That's a good question. So if the unit's at a reduced capacity and we happen to get an auxiliary heat call, it'll just drive the indoor fan motor to 100% airflow. But if the outdoor unit goes into defrost, it'll put itself into 100%. It'll put itself into 100% capacity, because when it goes into defrost, it drives it to 100% capacity outside. When it does that itself, it'll also generate a W output from the outdoor unit to bring the heat strips on inside, which in turn will bring the indoor blower to 100%. Does that make sense?
Right. So it's bypassing that kit that comes with for the ECM motor.
I kind of like the way you think there. That's exactly electrically and mechanically, that's exactly what's happening. So anytime basically we get a W call, either from the outdoor unit going into defrost or the indoor unit or the thermostat calling for auxiliary heat, it's going to drive that ECM motor to 100%. So we don't overheat the heat strip. Yeah. Good questions. Any other good questions or comments? Everybody good?
Have customers complained about the ramping up and down of the blower motor during heat operation?
Okay. So the indoor motor is ramping up and down?
Yeah, I'm just saying, has there been any complaints by any customers noticing the ramping up and down of the blower motor?
No, I've not had any complaints along those lines. As a matter of fact, most of the time, and this is important, and we'll talk a little bit about ductwork later. If you've got properly sized ductwork, most of the time these ECM type motors, variable speed motors and ECM motors, they share the same type of technology. Only the ECM motor, the standard ECM motor, has just got speed taps on it, where the variable speed motor, it's got a control board that you set up your airflow. But most of the time, if you've got properly sized ductwork, the units are so quiet you can hardly hear them. They're very, very quiet, very, very quiet units, very efficient units as well. Good questions. All right, fellas, let's take a look at. I want to throw this in. Now, do you guys do any furnaces and furnaces or dual fuel?
Very little.
Okay. Well, we'll kind of breeze through this a little bit, but basically what I've added to this is if you're going to do dual fuel, basically what we're going to ask you to do, because the outdoor unit by design generates a W signal every time you go into the heating mode of operation. And it generates that W signal for about 1 minute. And what that's for is that if you're hooked up to an air handler, that W signal brings the heat strips on. In the heating mode, it brings the heat strips on. And what that does is it kind of preheats the air, and it prevents or it reduces a cold blow condition at the initial start of the heat pump. And so when you take this outdoor unit that's designed to give you that W call every time you have a call for heat, for 1 minute, on a furnace, what can happen, it can cause the furnace to short cycle. That's the long and short of it. So basically the furnace comes on, gets a W call, goes through its heating sequence. It takes about 30 seconds before the flame comes on, and not the flame, but before the blower comes on. So now the thing runs for 15 or 20 seconds, then bang, it shuts the furnace off, right? And so you can short cycle the furnace. Now, we haven't had any reliability issues yet, but we don't want to have any reliability issues. So if you do a dual fuel, this is just a quick little overview. If you do a dual fuel, take one of those little cartridge dry out thermostats. You've seen them, the sheetrockers use them all the time. And what you're going to do, it looks like this, that little dry out thermostat. And what you're going to do, you're going to break the W signal from the outdoor unit to the W signal on the furnace. And then what you're going to do, you're going to take that little dry out thermostat there, that little construction thermostat, and you're going to break that W signal from the outdoor unit to the furnace, if you have a dual fuel. And then you're going to wire tie that little thermostat to the suction line on the evaporator coil, which is a hot gas line. Remember, on a heat pump, it's a hot gas line in the heating mode. But you're going to wire tie it and insulate it to the suction line on the evaporator coil. And then what'll happen, here it's wired in the circuit. So now what'll happen, as long as that line is warm, from the previous heat pump cycle, that thermostat will be open electrically. And so then on the next call for heat, it's not going to bring the furnace on or short cycle the furnace, cause the furnace to run for like 1 minute the next time it goes into heating mode. Because remember, the outdoor unit's designed to bring the heating on inside for about 1 minute, just to kind of preheat the air so you don't have a cold blow complaint. That's how it's engineered. And so if you do dual fuel to prevent short cycling of the furnace, throw one of those little construction thermostats in. You'll see how it's wired into the circuit right there. Everything wires exactly like it did before. It's just we're going to break that W signal from the outdoor unit to the indoor unit to give us the capability of to prevent or to help reduce short cycling of the furnace in the heating mode. So any questions or comments on that if you guys do dual fuel? Everybody good? All right, so that kind of rolls us into just using regular furnaces. Now, if you guys don't do a lot of furnace product, we'll kind of breeze through this a little bit. But basically, if you're going to put these on a dual fuel application with the furnace, remember, you're still going to use the relay kit. And the TME and the TMY furnaces are going to be, the TMY is a 2-stage heat, and the TME is a single-stage heat furnace. You're still going to use the relay. And please remember that if you're going to do a dual fuel, don't forget that your heat pump has to have that BO selection, but it also has to have dual fuel capability. And most of your modern heat pump thermostats can do dual fuel, but just remember, if you're going to do dual fuel, you have to have a thermostat that's going to be compatible for a dual fuel application. And so this is going to look very, very similar to what we did before. Like I said, I'll kind of breeze through all this, but you're going to use that little construction thermostat we just talked about if you're going to do dual fuel. As far as the wiring, like I said, it's going to look real familiar to you. We just did this. It's essentially the same wiring we did on the AE air handler, wire for wire. You'll notice that the relay hooks up the same, common and B, or I should say common and the other side of the relay coil. Common of the switching contacts goes to Y, just like we had before. Your normally closed contact's going to go to second stage airflow. Your normally open contact's going to go to first stage airflow. So basically, this wires up just like that AE air handler. It's essentially the same block wiring that we just discussed. It's just it's on a furnace now, and we have a dual fuel thermostat. And so any questions or comments on that before we do a little animation and go to a TMY furnace? Any questions on that?
Nope, we're all good.
Look good? All right, fellas, just remember then, on the TMY, which is a 2-stage furnace, it wires exactly the same, except there's going to be an additional terminal because it's a 2-stage heat. So basically, you'll have a W2 input for 2nd stage heat, and then your W/W1 will be for 1st stage heat. And so that's the only difference between the two furnaces as far as the low voltage wiring. In addition, when we go ahead and do the animation, you'll see that when we energize S1, just like we did before, we're going to switch that relay and command low airflow or reduced airflow when the outdoor unit says, hey, I want low airflow or reduced airflow because I'm at a point of modulation right now that will allow that airflow to be reduced. So any questions or comments on the logic of all that before we look at some variable speed stuff and then get into our HMCG straight cooling product?
So is the illustration that we're looking at right now, is that the exact same kit that we were, of the illustration that we were just looking at?
It is. Thank you for that good question. Yeah, so it's just going to be the 001 kit. Now, guys, the reason we recommend the reason we recommend these kits, I want to make something clear. We recommend the kit because of the supplied parts. It comes with a biflow filter dryer. It comes with the little relay kit. It also comes with some pre-made harnessing. Now, we had a contractor a while back make a comment, well, you know, I've got biflow filter dryers on my truck, and I've got peanut relays on my truck, and I've got low voltage wire that I can make up myself. Can I make up my own relays, and can I make up my own kit? Well, of course you can. And you know, if you want to just take a little peanut relay and hook up some 24-volt wires yourself, you know, make up your own little wiring, and put your own biflow filter dryer on there, let her rip, no big deal. It's just that these kits that we put together for you, the 001 and the 002 kit, it's a handy little kit that has the biflow filter dryer already in there. It's got some pre-made wiring harness for you, so you don't have to sit here and make up a wiring harness, or, you know, make up low voltage wires. And then it's got the little relay kits. So, I mean, you know, it's up to you guys, but don't think that you have to use that kit. If you've got your own biflow filter dryer on your truck and you've got some peanut relays, you can make up your own kit if you want to. It's no big deal. Just for convenience, we, you know, offer those kits. Any questions on that? Okay, so you guys can see, like I said, this is basically just a little peanut relay inside the unit for switching that airflow. Real simple. So guys, if we get into the variable speed, like an ABC air handler, you know, which is the older style air handler, or a TMV type of furnace, you know, we're going to go through this block wiring diagram again. Now, one of the things I would like you to notice, so we're not going to talk about the humidifier and dehumidifier terminals and stuff like that. You know, for simplicity, we're going to keep these block wiring diagrams simple. But just remember, on the variable speed product, you're going to have a dehumidification terminal and a humidifier terminal and a electronic air cleaner terminal and all that stuff that you can utilize those components. So we're going to be focusing on the relay setup as well as the, you know, low voltage wiring. Now, please remember, anything variable speed, you got to have the 002 kit, except our new variable speed air handler does not require it because the board itself can be configured on the air handler for this S1 input, right? But if it's like an older ABC air handler or any of the variable speed furnaces, you're going to have this 002 kit. Now, remember, if you're going on a furnace again, you got to have that dual fuel operation if you're going to be doing a furnace. But let's take a look at an air handler configuration. Now, this is a variable speed air handler. This is the older style air handler, but you're going to notice it's got 2 relays on there. The 002 kit has 2 relays. Those relays are designated RV and S1. So let's take a look and see how this is wired up. So just like we had before, B goes from the thermostat to the outdoor unit. W2 is our second stage auxiliary heat. W1 would be first stage auxiliary heat, and that goes all the way through like we had before. You guys, this is looking familiar to you. Y is your compressor call. C is 24-volt common. R is your 24-volt hot. G is your fan, just like we had before. Now, on the S1 relay, this is going to look familiar to the S1 relay and the RV relay. You're going to notice that the coils are going to go to, one side of the coil is going to go to common. You'd expect that, just like we had before. You'll notice that the B terminal, or I should say the other side of the coil on S1 relay, goes to S1, which makes sense. The common on the S1 relay is going to take 24 volts from the Y signal, just like we had before. The normally closed contact is going to go to Y2, second stage airflow. Normally open contact on the S1 relay will go to Y1, first stage airflow on the variable speed air handler. Now on the RV relay, that second relay, we're going to take the B terminal, or more specifically, the other side of the coil, and we're going to go tie it onto the B terminal. Now the reason is we're going to switch this relay. I want you guys to think about it. Now we'll show you the animations here in a little bit. But what we're going to be doing, we're going to be switching the RV relay anytime we have a heating call from the thermostat, calling for B terminal. We're going to tie it onto that reversing valve terminal. So anytime we're calling for heating on the outdoor unit, we're going to energize that RV relay. Now that RV relay, the common tie point, or the common terminal, switching terminal point, is going to grab Y, just like the other relay. And so the compressor is going to be running. We're going to be calling for compressor operation. We're going to energize the RV relay in such a fashion as you can see on the schematic here, the wiring diagram. And then the normally closed contact on the relay, the RV relay, goes up to O terminal. Now, guys, the reason we have to do this, just so you know, on the variable speed air handler and the variable speed furnace, the way the board is configured, the way it's set up, the actual control board on the furnace or the older style air handler, it has to see an O signal in the cooling mode for advanced functions. Let me say that one more time. On the variable speed product here that we're looking at, it has to see an O terminal in the cooling mode for some advanced dehumidification and some advanced motor ramping functions. So in the cooling mode of operation, right now we're in the cooling mode. So if we energized the thermostat right now for compressor operation, we would be in high speed airflow and the cooling mode because we have that O terminal energized on the indoor unit. Any questions or comments so far? Everybody good?
Earlier at the beginning of the presentation, I thought you said that O being energized would be heat mode and it defaults to cool mode.
I love the way you're thinking. And that's exactly correct. And so don't confuse the BO selection on the thermostat for heating mode on the outdoor unit reversing valve. This has nothing to do inside. This is strictly that RV relay is strictly for the indoor variable speed product to give it 24 volts on its own O signal inside in the cooling mode for advanced functions. This has nothing to do with the outdoor unit. So just like we had before, the thermostat has to be configured for B for heating. It's just that what we're looking at right now is the O terminal strictly on the indoor unit has to have an O signal in the cooling mode for some advanced functions. And that's the only reason that RV relays there is to provide 24 volts to the O signal on the indoor unit only, variable speed, for advanced blower functions inside. That was a good question.
So that's why they energize it in cooling mode instead of in. Is that the way why they have it configured the way that they have it outdoor or outside also, so that you have to energize orange to get cooling normally?
So you have to energize orange on the indoor product to get the cooling blower functions inside. Outside, with the outdoor unit, if it has no signal, if there is no O outside, there's a B terminal for heating. So the outdoor unit, if it doesn't see a B signal outside, a B outside for reversing valve, it defaults to cooling mode. So right now, as we take a look at that, if I switch my thermostat to cooling, or if I switch the thermostat on right now in the cooling mode, it's going to energize Y. It's going to it'll turn the outdoor unit on. The outdoor unit says, "Ooh, I've got a compressor call, but I do not have a B signal for heating." So right now I know I'm in cooling mode by default. And so right now, the unit right now, as you're taking a looking at it, it's in the cooling mode, high speed airflow, as you're looking at it right now. Now, let me go ahead and talk a little bit about the variable speed furnace, how it wires, and then we're going to do some animations for you so you can kind of see how all this works for switching airflow and switching the RV relay. So watch this for another minute or two. So on the TMV variable speed furnace, everything stays exactly the same, except the terminals. You'll notice that the terminals are a little bit different configured on the WW1 terminals. Is configured a little bit differently, and we've got that little construction thermostat in there to break that W circuit if you have a variable speed furnace, if you got dual fuel application going. But now watch this on those furnaces. Now again, remember that furnace has to have a dual fuel configuration on the thermostat. So just please remember that. But now let's go ahead and go back here and take a look at a variable speed unit switching. So let me do that animation again. So this is going to be the switching now of the airflow. So when the outdoor unit, variable speed furnace or air handler, either one, when the outdoor unit says, "Hey, give me reduced airflow," it's going to energize S1 just like we did before, bang. And you see that S1 relay switches. Now we're still in the cooling mode. It's just reduced airflow now. And so right now the unit is calling for reduced airflow. That S1 relay switched. We have reduced airflow and we're cooking along at reduced capacity. Everybody's happy. Now let's say, for instance, the thermostat says so the thermostat goes into the heating mode of operation. When the thermostat goes into the heating mode of operation, what it's going to do is going to energize B terminal. It'll then switch the RV relay, and it'll break that 24 volts to the O terminal inside. Because remember, the only thing that RV relay is doing on the left-hand side is when we go to the heating mode, bang, we energize B, you switch that relay, and you kill that O signal inside, because now the indoor unit recognizes the system is in the heating mode because it doesn't see the O signal. So the O signal has two functions on the indoor unit. We're talking indoor unit only now. The O terminal has two functions. Number one, it tells the unit, the indoor unit, that it's in the cooling mode. In addition, if the O signal is broken and I'm in the heating mode, it disables the cooling on delay ramping profile for humidity control and so on, right? So some of these advanced features on the indoor unit are driven by the O terminal on the indoor unit. So that's why we have that RV relay there. Let me back up. That's why we have the RV relay. In the cooling mode, we energize O terminal on the indoor unit. In the heating mode, bang, we break that O terminal to tell the indoor unit we're in the heating mode. Any questions or comments on the relay logic that we're looking at with these with the relays and the indoor product and the outdoor product? Any questions or comments on it?
Joel, on this is utilizing the relay. So if they have the JHVT, that would be different, correct?
That is correct, Emily. That's a good question. So if they have the JHVT, the brand new air handler, the new variable speed air handler, then all these relays go away and you configure the S1 output from the outdoor unit on the board itself. So on the board itself of the JHVT air handler, you've got some dip switches and some configuration that you can do where basically you're telling the indoor unit that you have an S1 input from the outdoor unit because it's hooked up to an HMH7, and you eliminate the relay pack altogether on the new variable speed air handler. That is correct. Good question.
Do you know if your typical application is going to be with the JHVT, or is it going to be more the ECM version?
It's gonna be more the ECM version or the TM80.
Okay.
Okay.
So you guys are going to be focusing in. Look at my cursor. You guys will be focusing in on that 001 relay kit, which is just a single relay, right?
Yep.
So that'll be your typical application then with a JMET air handler or a TME type of furnace. You'll just use the single relay kit, the 001 relay kit. Good. That's a good question, Emily. Any other good questions or comments before we have just a little airflow overview? I mean, a little airflow reminder on modulating stuff, and then we'll get into our straight cooling product, and then we'll roll into a little airflow measurement overview as well. Any questions or comments?
Looks like we're good.
Okay. Well, fellas, I just want to remind everybody on as far as airflow is concerned, remember the HMH7 is a modulating unit. And so we want to make sure that we provide the proper airflow on the unit, because remember, one of the parameters of the outdoor unit is looking at suction pressure, suction line temperature, liquid line temperature, liquid line pressure, discharge line pressure, I believe, and temperature, and outdoor ambient temperature. So it's looking at all these temperatures and making intelligent decisions on where it needs to be for capacity. So if I have inadequate airflow inside, undersized ductwork, whatever, what's going to happen is that evaporator coil is going to be cold with reduced airflow. It'll be colder than it normally would be if I have reduced airflow. And the indoor unit's going to, or excuse me, the outdoor unit's going to interpret that as a reduction in capacity. In other words, it's cooling off in the house, and so it's going to think it needs to start screwing back. So just remember, you want to size your ductwork for 400 CFM per ton of total capacity. So if I have a 2-ton unit outside, I need 800 CFM airflow. If I've got a 3-ton unit outside, I need a 1200 CFM. You cats get the idea. So ductwork becomes, more critical because we want to make sure that we have full airflow so the unit knows at what point of capacity it really needs to be working. In addition, don't forget that manual D, which is our ACA manual D, which is our airflow and duct design criteria when we build a duct system. This table right here is right out of manual D. And what it is, it's recommended duct velocities as well. So you not only have to have the right CFM, but make sure that your air is not moving too fast down your ductwork or your takeoffs. And these are just some examples, like on your main trunk or your home run or your main trunk. You're going to want to have somewhere between 700 and 900 maximum 900 feet per minute velocity down that main trunk. Your takeoff should be about 600. And 400 on the return. Registers and grills need to be about 500 and 400 on return. Diffusers are about the same. And remember, if you have a filter grill or if you have a return grill with a filter in it, don't exceed 300 feet a minute velocity across that filter. And again, all of this stuff is right out of Manual D. And if we'll follow these Manual D recommendations when we do our airflow and duct design, it'll keep us out of trouble. And so I always recommend to look at those things as well when you're putting one of these things in, and make sure your ductwork's in good shape and you've got the proper airflow, because it really can affect a modulating system really more than a regular non-modulating system. Because remember, the outdoor unit is looking at all these pressures and temperatures on the refrigeration cycle as well as outdoor temperature. and making intelligent decisions on where it needs to modulate or what capacity point it needs to be at. And so if you have reduced airflow, again, as a summary, if you have reduced airflow, the indoor coil is going to be colder than it normally would be under the same conditions of proper airflow. And the outdoor unit will interpret that as a reduction in capacity. So it might be, you might need 100% capacity, but it sees there's lousy airflow inside, so maybe it's only modulating at 85% capacity. You get the idea. So like I said, airflow becomes very, very critical and important whenever we do, our airflow and duct design on a modulating system. So with that, any final questions or comments on the HMH7 before I shut this screen down and we roll into our HMCG straight cooling product? Any questions or comments? Everybody good?
Joel, I know you're going to do fantastic. I do have a hard stop here at the top of the hour, so I probably have to drop. But
okay. All right. Well, I will go ahead and bring my screen back on. Let me go ahead and switch screens real fast. The next thing we're going to talk about is going to be the HMCG2, the straight cooling product, seeing as how we're kind of on the horizontal product.
Thank you, Emily.
you bet.
Absolutely. Thank you, Emily.
I'll hang out till the top, but I didn't want to interrupt when Joel gets going. Can't interrupt him on his flow sometimes.
My pal.
Joel, are you capable, or do you have the possibility at the end of the air movement to walking us through Navigator, show them how to get the momentum series training?
I could probably do that. We can stop the recording and we can do that for you as well. We should be able to find that for you out there.
Yeah, and I think I sent a screenshot as part of the meeting invite on where to find it, but it's sometimes, you just got to search for the right keywords.
All right, team, at this time, let's go ahead and jump into our HMCG2 horizontal overview. And what this is going to be all about, it basically looks a lot like it actually looks the same as the HMH7. It's just that it's a straight cooling variant of the product. And remember, it comes in 2, 3, 4, and 5 ton variants. We have some pretty nice outdoor minimum max temperatures, like we said before. On this particular product, it's 50-degree minimum outside for cooling and 122-degree outside for cooling. It's a straight cooling product. And so again, those are pretty nice temperature range there on the cooling product. In addition, kind of a little news flash, the HMCG2 has a factory charge pre-charge on the outdoor unit for 25-foot line set. Now, this is kind of different. Most of our Champion equipment, with the exception of this, on our residential, we pre-charge them for enough refrigerant for a 15-foot line set, So this product right here is actually set up with a pre-charge for 25-foot line set. So that's pretty nice. As we take a look at it, just to kind of so you can kind of visualize where this is in the lineup, we see we have our AL 21 and 19 product, and then the HMCG2 sets kind of right in the middle of the stack, and then we've got some other products as well, 15.2, 14.3, and a 13.4 for northern regions on our straight cooling product. So we see that the HMCG2 is right there in the middle, a 2 through 5 ton inverter drive with just conventional 24-volt wiring. So kind of right there in the middle of the stack. Now, as far as wiring goes, we're going to go ahead and do some simplified block wiring diagrams just like we had before. Now, this will be a little bit faster than the HMH7 because we do not have a relay on any of the products. So basically, we don't have to worry about a relay kit. And we're going to be wiring the HMH7 directly to the indoor unit, the HMCG2 directly to the indoor unit for airflow management. And again, we're going to be using just a conventional 24-volt wiring scheme and function. So as we take a look at it, you know, it's kind of a simplified block wiring diagram, but you can notice on the outdoor unit that we don't have like the B terminal and all that because it's a straight cooling product, so we won't be utilizing like a B terminal or anything like that. So if we do have an ECM type of air handler, this would be like an H or a JHET air handler or the legacy AE air handler. W2 will be second stage auxiliary heat. W1 will be first stage. This is looking familiar to you. It's going to wire exactly like we had before. Again, it's just a straight cooling product. You'll notice that there's a Y, goes straight outside. C is 24 volt common. R is 24 volt hot, and it does not go to the outdoor unit just like we had before. And then on the G, you'll have, that's your fan call. Now, typically what we're going to do, just like we did before, we're going to have G will be our lowest speed tap, is how we typically find that hooked up. You'll also notice that on the high speed tap of the ECM motor, go ahead and grab your auxiliary heat. So again, we're going to drive the auxiliary heat fan speed to 100% airflow, or, you know, high airflow, so we don't overheat the heat strip. Now watch this. This is exactly opposite of the heat pump. I want you cats to catch this now. The ECM motor, we're going to select a 100% airflow on S1. Now remember, on the heat pump, S1 commanded low airflow. On the straight cooling product, it commands high airflow. I want you guys to wrap your head on that. So the outdoor unit is directly affecting the speed of the indoor blower motor without a relay. So S1 on the outdoor unit, the straight cooling product, it's exactly opposite of the heat pump. Well, Joel, why'd they do that? I don't know. That's just how they did it. S1, it commands 100% airflow. You'll notice that the Y terminal is going to come down directly to the motor. And the Y terminal, anytime we call for compressor operation, the Y terminal is going to command that 60 to 65% airflow. So when you take a look at the straight cooling product, just standard airflow, just sitting there, is going to be 60% airflow, 60 to 65% airflow. So when this unit comes on, it's automatically going to default to the lower airflow. Then what's going to happen when I get an S1 call from the outdoor unit, that's going to go inside that 24 volt signal, and it's going to command 100% airflow. It's exactly opposite of the heat pump, and there's no relay at all. So is there any questions or comments on how that scheme works?
Can you go back to the last clip where you had the ECM motor tapped into W1? So what happened from there to the next clip? Sorry, I was writing something down.
That's okay. So this is going to be in case you have an auxiliary heat call, you're going to select a speed tap. Let me back up here. So you're going to select a speed tap for high speed tap on that auxiliary heat, and then your 100% airflow, you're going to go to S1. So whatever speed tap you're using for 100% airflow, you're going to tie that onto S1. And then off your yellow wire, you're going to tap off of that, and you're going to go to the motor for your 60 to 65% airflow on your yellow wire. So what happens is right now, when the unit's in the cooling mode of operation and it calls for cooling, it's going to be 60% airflow. However, when the outdoor unit says, hey, I'm at 90% capacity or whatever, actually it's about 70% capacity, it'll generate that S1 signal and drive the indoor unit to 100% airflow. So from about 70 to 100% capacity, you're going to have 100% airflow. So the whole theme here with the outdoor unit, the straight cooling product, is we're letting the outdoor unit directly affect the airflow inside without the use of a relay. Any questions on that?
Looks good, Joe.
Okay. So if we look at a TME and a TMY furnace, it's going to be essentially the exact same wiring we had before, except the terminals are going to be looking a little bit different. We're going to have a W terminal on a TME because it's single stage. Yellow goes all the way outside like we did before. 24-volt common goes all the way through. R terminal is 24-volt hot. G is fan. Now you're going to notice something, because it's a furnace, we've actually got hard terminals on there, say Y1 and Y2, right? So Y2 is going to go up to S1. Y2 will go to S1 because that's our high-speed airflow commanded by S1. And your Y1 terminal will go right up to the yellow wire going to the outdoor unit. So basically, when the thermostat calls for cooling, it's going to call for 60% airflow Y1 on the unit. And then when the outdoor unit says, hey, I'm at a higher capacity, it energizes, excuse me, I guess I showed the TMY furnace. It's the same thing. We got a little out of sequence there. So the TMY furnace is going to just have 2 stages of heat. Other than that, it's going to be wired exactly the same. But then when we go to the outdoor unit, we energize S1. Again, we're going to bring on our second stage cooling airflow. So let me back up again one more time. So the default airflow on the HMCG2, the straight cooling product, the default airflow with the unit just sitting there and it calls for cooling is 60% airflow. Then when the outdoor unit has been running a while and it says, hey, I need increased airflow because I'm at a higher capacity, it energizes S1 and drives the indoor unit to second stage airflow. So that's an important concept we have to remember, that on the straight cooling product, the outdoor unit S1 output directly commands our second stage airflow. Any questions or comments on how we're using that logic?
How do they get the load on the outdoor unit, the capacity that's at? How does it figure that?
Okay, so that's a good question. So the outdoor unit, as you can see, it's a very, very simple 3-wire, in this case, simple 3-wire 24-volt wiring. But the outdoor unit, what it's doing, it's constantly monitoring the suction line temperature, liquid line temperature, hot gas line temperature, so it knows what the capacity on the refrigeration circuit is. It's also comparing that to outdoor ambient temperature and thermostat activity. So if the thermostat's calling for cooling operation and the outdoor ambient is whatever that is, it's all proprietary engineering inside that board, you know, the algorithms inside that board. So we have thermostat activity, it's calling for cooling. The outdoor temperature, say, is 85 degrees. I'm just making this up. The outdoor temperature is 85 degrees. Suction line temperature is, 49 degrees. Liquid line temperature is 121 degrees, whatever. It's comparing these temperatures on the refrigeration circuit as well as outdoor temperature, and then it makes intelligent decisions on at what capacity it's going to be driving the compressor to. Now, the compressor will modulate between 35 and 100% capacity based on what the board tells it what to do, right? But the board itself, the control board outside itself, is actually taking all these temperatures on the suction line, the liquid line, the hot gas line, outdoor air temperature, all those parameters, and deciding and making intelligent decisions on what point of capacity it needs to be. And so, and then when it's at the appropriate point of capacity, like 60% or more, it'll generate an S1 signal and tell the indoor unit, give me full airflow. But if it's below 60% capacity, let's say it's at 42% capacity, I'm just making that up because it's a real mild day, then what'll happen, it'll drive the airflow inside. It'll kill that S1 signal, and then the airflow drops back to 60% airflow on the indoor unit. So here's the another way to look at it. The indoor unit is giving you two airflow speeds, 60% airflow, 100% airflow. The outdoor unit is modulating between 35 and 100% capacity based on all those parameters I just talked about, looking at sensor temperatures and liquid line temperatures and all that stuff. So the outdoor unit's just sitting there by itself, just figuring out what capacity it needs to be, based on all the temperature inputs it sees. The indoor unit is just real simple, either 60% airflow or 100% airflow, based on that S1 signal that's coming in from outdoor unit to call for second stage airflow.
Cool.
Good question. Any other good questions on that? Okay. Well, fellas, on the variable speed product, you still don't have to have a relay. Still 24-volt wiring. But you're going to notice now we've got this variable speed air handler that's going to be a setup for air conditioning, not heat pump. So please make a note of this. On a variable speed air handler or variable speed furnace, you're going to have a dip switch on there that's going to say heat pump or AC. Make sure you flip that little switch that says AC. That way it ignores the O signal, okay? And so remember, the O signal is an important part on the heat pump if you're hooked up to a heat pump, but on a straight cooling product, the variable speed product inside on a straight cooling does not have to have an O signal. But there's a little selector switch or a little jumper on the board itself that says heat pump HP or AC for air conditioning. Make sure that little jumper, that little dip switch is on the AC position. That way, the indoor product ignores the O terminal on the indoor product. Other than that, it's pretty straightforward. W2 would be your second stage auxiliary heat. W1's your first stage auxiliary heat. Y terminal's your compressor outside, just like before. C terminal goes all the way through, common. R goes from the thermostat to the indoor unit. G goes from the thermostat to the indoor unit. R does not go outside. Y2 is going to go up and grab your S1, just like we had before. Y1, first stage airflow, will be tied onto your yellow wire going outside, so that basically anytime the unit calls for cooling, it'll be at 65% airflow. And as far as the air handler is concerned, you'll see the wiring on the furnace. If you have like a variable speed furnace, it wires exactly the same. The only thing you'll notice is that the terminals are slightly labeled differently. So you'll have like a W/W1 for your first stage heating on your two-stage furnace. But just like we had before, guys, when you go into high airflow command, you energize that S1 signal, and it brings the indoor unit on second stage cooling airflow. So the straight cooling product is very, very straightforward. I mean, it's very simple. You'll notice you just have 3 wires going outside. That S1 wire to command second stage airflow, yellow and common going outside. And you get all that functionality. Any questions or comments on how the HMCG2 wires up with the indoor products that we talked about? Any questions or comments?
We're all good.
Well, fellas, let me ask you something. Did everybody get some little handouts for the airflow overview?
Yes.
Okay. The airflow overview, I like to give guys a break about every hour and a half, but the airflow overview is probably going to only take about 15 or 20 minutes. You guys just want to press on and do that, and then maybe take a little break, and then we can look at Navigator.
Yeah.
Want to do that? Okay. Well, let me go ahead and this is just a repeat of what we did before. Just remember, airflow is going to be important on any variable speed, or I should say any modulating unit. We want to make sure that we've got proper airflow, just like we had before. I just had that kind of tagged on the end of that as well. So let me get this. Give me 2 seconds to kind of get this other little thing up here. This little airflow measurement overview. Let me pull that up, and then we'll get you guys squared away on the. Okay.
They stopped recording now, right?
All right, guys. As I'm pulling up this little airflow overview here, I'll let you guys kind of be my monitor here. Can you guys see the screen okay?
Yeah.
All right, now you said you did get some little handouts, right? So we can kind of follow along on that.
Yes, sir.
Okay. So fellows, in this portion of our training this morning, we're going to go ahead and do an airflow measurement overview. And so this is actually part of our airflow and duct design class, but I'm kind of skipping, over all the duct design because, I was asked if we could just do an airflow overview. Again, a quick reminder that when you're designing a duct system, make sure and really look at this manual D velocity table, because velocity is important, is a very important consideration when you're taking a look at airflow, because if the air is going too fast, it's going to be noisy. In addition, if it's going too fast, the heat exchangers aren't going to be able to exchange that heat properly. So just remember, we're going to recommend that you follow these velocity tables whenever you're designing a duct system. And please remember, on a filter grill, if you have a filter on that filter grill or behind that filter grill, do not exceed 300 feet a minute velocity across that filter. That's manual D recommendation. Okay, so all of our factory airflow charts, fellows, are set up for what we call external static pressure. Now, external static pressure is going to be found by looking at supply static and return static. So remember, the fan is designed to move air through the duct system by providing a positive pressure on the supply side and a negative pressure on the return side. So to measure external static pressure, or what we also call ESP, you're going to measure the supply side static pressure, and that's going to be a positive number, and write that down and remember it. You're going to measure the return side static pressure and write it down and remember it. And then you're going to add those two values together to get what we call external static. Now, the way to think about external static is it's whatever is external to the fan. In other words, how much duct work and how much grills and how many components and how many elbows does the fan have to blow against on the positive side? So all the components on the supply side of the duct system is going to have resistance to the airflow, so the fan's going to have to blow against that resistance. And then on the return side, you're going to have filters and return grills and maybe some duct work. So on the return side, you have to be thinking about what components, what in the airstream is the fan going to be sucking against. So what we're really looking at on the fan, external to the fan, what's it blowing against and what's it sucking against. And that's really what external static pressure is. It's how much energy the fan's using to blow air down the supply and to suck air back on the return. And so that's what we're actually looking at when we're looking at ESP, also called external static pressure. So to find external static pressure, we're going to have a digital manometer, or you can have the old magnehelic gauge. But most people nowadays use what we call a digital manometer, and this is just an example of one. There's a lot of different brands out there. I just happen to have a field piece in my tool bag, and so that's what you're looking at, is a field piece. You'll notice that it's a digital readout. You'll also notice that there's two different ports on this, P1 and P2. So you're going to select which port you want to use and make sure you hook your hose up to the port that you're using. And I recommend just use one port by the way, and we'll show you why here in a second. Some people like to use both ports and take supply and return static at the same time. I like taking them separately and adding them together. And the reason I do that, I think you get a better rating. It's more stable. Because let's think about it. If I had a turbulent air source on the supply and a turbulent air source for whatever reason on the return, now I'm trying to find, you know, the pressure between two turbulent sources. However, if I take them individually and reference one side to the atmosphere and the other side to the, you know, to the static pressure, and then add them up, you actually get a better reading, in my opinion. So I just like to use one port. So select which port you're going to use, P1 or P2. You're then going to zero the meter, make sure the meter is zeroed. And then you're going to come here and you're going to attach your hose to whatever port you're using. And then the other end of your hose to your static pressure probe. Now let's take a look at that. So this is what a static pressure probe looks like. So what it is, you've seen these are what they call static pressure probes, and it's used to provide that static pressure to the manometer. Now you're going to notice the airflow has to be pointed into the pointy end of the probe. So, you know, always make sure that the pointy end of the probe is into the direction of the airflow, and then you're going to attach the hose to the back of that little hose barb right there on the static pressure probe. And these static pressure probes, by the way, come in all different sizes and lengths, I should say. And, you know, the typical one that you're going to use most times is going to be about 6 inches long. But if you're on a big commercial job, you might want to have a longer one to get that probe a little bit more towards the center of the ductwork. So ideally, you want to be about, you know, you want to be into the ductwork 6 or 8 inches, whatever, and make sure that the air is always blowing against the pointy end of that probe. And then what you're going to do in this graphic example, you'll see that I'm going to take that static pressure probe and I'm going to put it in. I'm going to just drill a hole in the ductwork, and I'm going to slide that static pressure probe in, and I'm going to look at the supply and the return static pressure. So we read supply side static on the supply, return side static on the return, and then we add those two values up to get external static pressure. And this is how the airflow charts work on our factory airflow charts. So as we take a look, go ahead and grab your airflow chart that says JHET. And you're going to notice these airflow charts, they all have the same type of theme. They all have the same type of look and feel and theme. So step number one, you're going to determine what model of air handler you're looking at. So step number one, you figure out what model you're looking at. Step number two, you're going to determine what speed tap you're on that motor. And so once you determine the model and the speed tap, you know, you actually look at the speed tap and see what speed tap you're on. You then measure your external static pressure. Let's say in this example, it was 0.4 inches of static total. You then correlate, or you swing over from your model, your speed tap, and then your static pressure, and you correlate that number. In this example, that B24C on medium speed tap at 0.4 inches of static is blowing 625 CFM through the cabinet. You'll also notice right below that it says 95. That's the wattage that motor is pulling at that airflow measurement. So we're going to do some examples here, but I just want to make sure you guys, before we do that, make sure if you have any questions on the airflow chart, how this is working. Any questions or comments? Okay, let's go ahead and do some examples then. So referring to your JHET airflow chart, you're going to notice this first reading, and I have to apologize. I can't get rid of this little screen, this little Teams meeting screen. I can normally move it up out of the way, but I can't. So you're going to have to tell me what's the manometer reading right now. Can you tell me?
0.32.
Okay, so go ahead and write that down or remember it. And so And and so on your JHET air handler chart, find the B36D model. It's on medium speed or medium high speed tap. So find B36D, medium high speed tap, and our supply static pressure, you said it was a 0.32, so write that down and remember it. Okay. And then we're going to take our return air static pressure. And that looks like it's about a 0.18. So 0.32 plus 0.18 equals what? Okay, good. Now, guys, this is important. You don't have to do algebra here. You don't have to do like a negative number and a positive number. You just add the numbers up. So 0.32 plus 0.18 equals a 0.5 total. And it's a B36D on medium high speed tap. So what's the CFM off that chart?
1225.
Okay, good. 1225. That's what I had too. So this is probably a 3-ton air. It's a 3-ton air handler. It's probably hooked up to a 3-ton unit outside. So if I'm blowing 1200 CFM or 1225 on a 3-ton unit, how do you feel about that?
Good, that's good.
Okay, good. So again, kind of put this in your back pocket. We always want to design our ductwork and all to provide 12, like our 400 CFM per ton. And so in this example, on a 3-ton unit, we're looking for about 1200 CFM. So we're right in there, right? So that's in good shape right there. Let's do another one. Let's say we have a B30D on high speed tap. So find that B30D high speed tap. Our supply static pressure is a 0.61. That's pretty high. It's real high, as a matter of fact. So write that down, 0.61, or remember it. And our return static is 0.18 for a total of, so 0.61 plus 0.8 equals what? So there you go. So 0.79. So referring to your chart, what kind of airflow are we moving on that B30D on high speed tap, 0.79 inches of static pressure? What's the CFM?
925.
Okay, now you guys are going to notice something. I had 930. That's close enough. But you guys are going to notice something. You know, that's pretty high static pressure. Now, even though these blowers are, you know, they're a heavy duty blower, and I mean, we've got lots of capacity. Fact is, if you take a look at the chart, you know, we have some pretty high numbers on those charts. But I'm going to tell you guys a little secret. For the most part, most manufacturers, they like to see their equipment running at about a 0.5 or a 0.55 total. And so this is another reason, by the way, I like to take my static pressure reading separately. Where am I having the most resistance on this unit, on the supply or the return side? Yeah, so again, that's why I like taking them separate. So I have 0.61 on the supply, 0.18 on the return. So the return looks like it's nice and open, but on the supply side, even though we're blowing the CFM, you know, as you guys can see, you know, the static pressure is pretty high. And look at your chart again, you're going to notice the wattage is pretty high too, isn't it?
Yep.
And so this blower is working really hard to overcome that duct static on the supply side. And so if I was going to remediate this, and here's the homeowner complaint, you know, I love your unit, but it sure seems noisy. It sounds like it's whistling out of the register, you know, where the air comes out. And so we've got some pretty high static pressure on that supply. And if I was going to remediate this duct system, I would start looking at the supply side, because that's where the highest static is on this. All right, so look at your TME airflow chart on your furnace. Guys, it's the same thing. Step number 1, you find the model number. Step number 2, you determine what speed tap you're on. Step number 3, you find the static pressure and correlate it to the appropriate CFM. Same thing, but we'll do some examples just to make sure you guys have got all this. On the TMY furnace, same thing. You find the model number, speed tap, static pressure, CFM. Okay, so we're going to do some furnace examples, and then we'll answer any questions we have for you. Then we'll stop the recording. We'll take a quick break. We'll come back and do a little navigator training with you. See if we can't find out some of those navigator questions for you as well. Okay, so this one here, this particular furnace is a TME060 B12 on medium speed tap. So find that on the chart. And by the way, if you guys will look at the graphic real quick, you see right here, I want you to notice something on the furnace. This is real important. Look at my cursor. On the furnace, the coil is not included on that chart. So what you're going to do, you're going to sneak in underneath the coil and take static pressure as it comes off the fan and just slide it underneath the coil if you can get it under the coil. So that's just remember the coil is not included on that airflow chart on the furnace product. So our static pressure on the supply side is a 0.32 on it. This is a TME 060 B12 medium speed tap. 0.32, just write that down and remember it. On the return, it's a 0.18 for a total of 0.5. And so what's the CFM on that TME 60 medium speed tap at a 0.5 inch of static? What's our CFM?
1050.
Okay, good, excellent. All right. Good. Any questions on that? All right, let's do a couple more just to make sure we've got this. Here we have a TME 100C16 on high speed tap. Supply side static is 0.43. Return static is a 0.14. So 0.43 plus 0.14 equals what?
5.7.
Okay, good, excellent. And so now the reason I did this one here, guys, is because I want you guys to extrapolate a little bit. It kind of falls in between two values. And so it's not a 0.5, it's not a 0.6, it's a 0.7. So what would you call the CFM? You're kind of extrapolating off the chart.
1610. Yeah.
Okay, all right. I had about 1600, 1610, something like that. And the reason I did that, again, is just to kind of show you guys that sometimes you have to kind of extrapolate off the chart. But remember, if you're within, 50 CFM, 25 to 50 CFM from chart value, you're right in there. From a field application, you don't have to be, down into 2 or 3 CFM range, especially on this particular furnace. That's a 4-ton drive. That 16 means it's 1600 CFM drive on that furnace. And so, I mean, if you're, if you're 1605 or if you're 1590, you're close enough for all field application. Any questions on that? Okay. Here's a TMY, TM9Y 80C medium low speed tap. And we've got a 0.32 on the supply. And a 0.43 on return. So let's add those up. And what's our total static?
0.75.
Okay, 0.75, which is getting pretty high, isn't it? And so we're on medium low speed tap and we're still running, 0.75. What's our CFM?
855.
Okay. Okay, good. I had 850, close enough. Now, let me ask you cats a question. Where's the problem on this return? I mean, where's the problem on this system here? Is it supply or return where we have the problem? Yeah. You got 0.43 inches on return. That's a lot of static on the return. Guys, put this in your back pocket. Again, one of those little things that I like you to keep your brain engaged on. You want about 70%, 60 to 70% of your static, the energy of that fan doing the blowing, not the sucking. Because the supply side is the high energy side of the fan, and we want about 60% or 65% or so of the energy of that fan moving the air on the supply side. So this is exactly opposite. We have most of the static pressure on this job on the return. So where I would start looking at remediation would be to get a bigger return, cut in an extra return, increase the size of the return. You guys get the idea. Another thing to consider is if the homeowner is insisting on using pleated filters, like those little 1-inch pleated filters, you're going to need more return. And so this unit right here might have been okay, but now the homeowner, they went to the hardware store and they bought some of those little cheap 1-inch pleated filters thinking they were doing something, but they're actually killing their equipment. And so kind of keep that in mind. You can, but return is really important. And in this case right here, the return path is where we're having our issues on the return. Guys, one other thing I wanted to kind of throw at you quick in this airflow measurement is it's kind of an old method of doing airflow. It involves a little bit of math, and we'll kind of breeze through this. But basically, if you've got a voltmeter and an amp probe, you can energize your heat strips like on an air handler, and select the speed tap that you're wanting to check. You can then multiply your measured volts times your amps times a mathematical constant of 3.414. And then you can measure your supply and return air temperature, plug a little math in, and get your CFM by looking at volts times amps times 3.414. That gives you the output portion of the formula. And then plug in a little bit of math, take your supply and return air temperature, plug that in, and then get your CFM. So this old temperature rise method is very reliable. It's kind of a backup method. We really want you using the airflow charts, but I just wanted to toss this out at you, that this airflow measurement can also be done with an amp probe and a voltmeter and a temperature probe. That's how we used to do it in the old days. Who's ever used this temperature rise method? Okay. So I didn't give you guys a formula page today. This is just a little blurb. One of these days, if you guys want to do like an airflow and duct design class, we'll go through more of that. But the big thing today, I just wanted to make sure that you were very comfortable looking at wanted to make sure you guys were very comfortable, looking at the factory airflow charts, and any questions or comments on how we measured airflow utilizing the factory charts today. All right, guys, I'll tell you what, I'm going to go ahead and stop the recording at this time. I want to thank you, by the way, for spending some time and doing some training with us today. When we come back from break, we're going to go ahead and jump on Navigator, but I'm going to go ahead and stop the recording at this time.